Hello everyone. In this video, we talk about support vector machines or SVMs. Support vector machines are supervised machine learning methods that they can be used to solve both classification and regression problems. And I'd like to emphasize this point because many textbooks and different resources, they mainly talk about support vector machines for classification because that's kind of like the easiest way to understand them. However, support vector machines can be applied to solve regression problems, and we have one example at the end of this video to show you how that can be done using scikit-learn. So before going into details, the question we want to answer is that why should we learn support vector machines? These methods are very helpful when we are working with high dimensional spaces. This means that when we are working with a lot of features, remember that when we have a labeled or supervised data set, we have, let's say, n data points and they live in some d-dimensional space where d is the number of features. And if d is very, very high, like let's say you have 100 or 1000 features, then things such as support vector machines are very helpful. In addition, support vector machines are very also helpful when we have limited number of samples. So although in many cases when you're working with text data or image data, we usually have access to thousands or hundreds of thousands or millions of data points. In many cases, especially medical domains, we may only have information about, let's say, 100 patients or so, or in some cases, a few tens of patients. And in these cases, support vector machines are actually very helpful. And then the other nice thing about support vector machines is that they can solve both linear and nonlinear problems. So we will discuss this in a little bit, that we have something called a kernel function when using support vector machines. And depending whether based on the fact that kernel function is linear or nonlinear and what type of nonlinearity it has, meaning polynomial or radial basis function, we can find all sorts of different functions that represent, for example, decision boundaries in a classification problem, or even in a regression setting, we can have different types of function that they can represent the underlying data patterns. So without further ado, let's go through problem formulation for support vector machines when we have a binary classification problem. We focus on this first because this is the simplest setting and we can talk about the main concept behind support vector machines, which is the idea of finding a margin and then trying to maximize this margin. So in this case, we assume that we have, as we said, a binary classification problem. We have two labels. When we talk about logistic regression, we assume that these labels are zeros and ones. But we know that the numerical values here, we don't care about them because we are just using these numbers to differentiate between the two classes. And therefore, when we work with support vector machines, it's very common to call one class -1 and the other one +1. And you will see that this really helps us to simplify mathematical derivations and computations for support vector machines. So in the simplest case, when you have a support vector machine classifier or SVM classifier, you have a function f that for any input x, so this is your input feature, it calculates a value or returns a value. And then we look at the sign of that value, meaning that if f of x is greater than 0, then the sign is +1. And if f of x is less than 0, means that it's negative, so the sign is -1. So this h of x here technically is that label that we predict, which is either -1 or +1. So you can see immediately why we're doing this, right? So we want to be able to use this sign function here as a way of converting this f of x to the corresponding labels. Previously, when we had logistic regression, we used sigmoid function or logistic function, and we went through all the math to show how we can convert a real valued function to those labels. So that's what we did there. In the case of support vector machines, we start with this sign function to give us the predicted label. And then we have to talk about this decision boundary f of x. And we call this decision boundary because if f of x equals 0, then means that that's exactly the point that separates the two classes. And then if we slightly move to one side, then that's +1 class. And if we move to the other side, is the -1 class. And for simplicity, let's say that this decision boundary is a linear function of the input feature. So in this case, we have this W transpose X plus B. And we know that this W has elements like W1, W2, W3. So for each feature X, we do have one corresponding coefficient here, or weight. And then this B is the bias term. And since support vector machines is kind of like a geometric technique, it's also interesting to think about W and B a little bit differently than when we were looking at linear regression. You can think of this vector W as determining the orientation and the steepness of this decision boundary, right? So in the very simple case that X is just, sort of like a scalar, then we know that this W is going to be the slope of that line, right? So in general, even if we have like hard dimensional spaces, let's say X might have like 10 elements, still this W tells us the orientation and the steepness of this decision boundary. And B is the bias term, right? Or in other words, it controls the position of this decision boundary relative to the origin. If B equals 0, then means that this sort of like, this f of x equals W transpose x. When x equals 0, then f of x is always 0, which goes through the origin. So now let's get a little bit more technical. So what is this exactly W transpose x plus b? Because we want to look at this from a geometric perspective rather than just a weighted sum. And so this is what is called a hyperplane, right? So a hyperplane in general is a flat subspace that separates the entire feature space into two distinct regions, right? That's what we said. We have this +1 class and -1 class. So this line separates the entire space into two distinct groups. And in the case that we have a two-dimensional space, a hyperplane is basically a straight line. If we have a 3D space, XYZ, then a hyperplane is a plane, right? So a plane that is technically two-dimensional. And we can extend this to higher dimensions too, using the same sort of like strategies. But for now, we mainly think about this in like 2D or 3D spaces. And especially if you're in a 2D space, right? So meaning that we have like only like X, which has X1 and X2. So those are the XY axes. Then we have a straight line. And here also for completeness, we have the definition of the sign function. So depending on whatever the input to this function is, these are the possible outputs. So we mainly want this +1 and -1, which depends on what f of x is returning, right? So based on that, we again divide this space into two distinct regions. So making predictions using support vector machine classifier is very easy. You just find f of x and apply the sign function, and you find the class assignment or membership. How about the other part of this, which is training this classifier? That's something very important. And in this case, we have to find the optimal values of W and B, right? So W and B, they determine this hyperplane. And that's exactly why I said that this becomes a little bit like geometric, because right now you can see that you have two different classes, the circle and the square class. So there are all these different lines, like the blue one and red one, or hyperplanes here, because we can talk about higher dimensional spaces too, that they separate these two classes. But which one is the best? So you can see that, for example, this red one here is not so great because it gets too close to some of these training data points. And the goal here is to differentiate between them. Whereas this blue one seems to be actually really nice because it kind of like keeps some minimum distance from both sides. And that's exactly the idea of this margin. So margin, the definition is the shortest distance between this hyperplane and closest data points from both classes, from both sides, right? So that's the closest from here, and there's some of them here, and that's the closest here. So this distance, which I show using gamma, is the margin. And so how can we train a classifier? By maximizing this margin. And remember, this margin we have on both sides, right? Because we want to make sure that we keep as much distance as possible from both sides of this hyperplane. So the main thing that we really do for the next few minutes is to explain how to find this margin mathematically and how we can optimize it. Before doing this, also I want to introduce you to this notation, which is support vectors. So these the closest points that we have on both sides, these are called support vectors, and that's why these things are called support vector machines. And this is why these support vector machines work very well with limited data, because what they need to do is to find these closest points on both sides, and this can be as easy as finding one point on one side and one point on the other side, and then they can draw these kind of like three lines, right? So the decision boundary and the two sort of like dotted lines that you can see, that we aim to avoid having any data points in this area. I like to think of this as a street, right? So think of this as a two-way street, right? So you have one way, the cars going this way, one way here for the other cars going to the opposite direction. And we don't want to have anybody to be in this sort of like a street and everything to be outside this street. That's the way I like to think about this. So how can we find this margin? So remember, the hyperplane has this equation, the set of all x's where W transpose x plus b equals 0. And now let's say you have a data point x that you want to find its distance from this line. What you do this orthogonal projection, right? And this perpendicularly projected data point here, we call this xp for projection. So now we need to kind of like, define the distance. So the distance is this perpendicular distance that we have from x to this hyperplane. And we can use a very simple sort of like, identity here, that xp, so from origin to this point xp, so that's a vector, plus d, so that's sort of like that perpendicular part that connects x to its projection, is equal to this point or vector from 0 to x. So xp plus d equals x. And you can think of this, I put here like this vector notation to show that we understand what we are doing here. And this tells me that this xp here, if I send d to the other side, is x minus d. So put everything together, we project point x perpendicularly onto this hyperplane, and that's called xp. And xp is technically x minus d. And d is that shortest vector from x to the hyperplane. So it's important to have this 90-degree angle here. Something else also remember to know is that when we have this w that we set from our hyperplane, so that's kind of like our normal vector too. So meaning that w is also in the same direction. So because of that, we can say that this vector d is actually alpha, where we don't know what this alpha is a scalar, times the vector w, right? So these two things are in the same sort of like direction, but the length of it really depends on this alpha. The other piece that we need to know is that this projection here, this xp, also lies on this hyperplane, right? Because that's the projection of x on this hyperplane. So meaning that W transpose x, now we have xp plus b equals 0. So what we really do here, in this equation that we have here, we substitute xp because this holds for all x's on this hyperplane. So we have W transpose xp plus b equals 0. And now we can see how we can use these different things that we have here to find this sort of like length of this vector d. So W transpose and xp is x minus d, and d is alpha times w. And this is great because now we can do the multiplication. So we have W transpose x W transpose W. And remember, for any vector X or W, W transpose W is equivalent to the norm or length of that vector squared. And then we have plus B here. So if we solve this for alpha, because what we really need to find here is this alpha to be able to find D. And this only depends on W and B, which means that if we know what W and B's are, so we have this alpha, right? And there's one more step, right? We care about the distance, which is the length or norm of this vector D. And by what we have here, D is equal to alpha times W. And a scalar times a vector, it's easy to find its length. It's the absolute value of that scalar, because just in case alpha is negative, we don't want to have negative distance, so we have to take the absolute value times the length of W. Which means that the only thing we really need to do is multiply this alpha by the norm of W, and remember this denominator is the norm squared. So we get rid of one of these 2's here, and so we get this formula. So the distance of any point X, like this, to this hyperplane, if you care about this distance, that's simply W transpose X plus B, meaning that substitute X into that formula we have for hyperplane, and this is not 0 anymore because X is not on that line, and if it is, then it's 0, obviously, but in this case, we want to find the shortest distance of a point which is not on that hyperplane. And then we have to also divide that by square root of, or by just the norm of W. Or in other words, a square root of W transpose W, right? Because again, W transpose W is norm square. So if you want to get rid of that square, you have to take the square root of this, or just simply use norm of W. So all in all, what this means is that if you have a data set that consists of n data points, and you want to find this shortest distance, you have to find this margin for all of them, and then you find the minimum value, right? So in this case, it means that the shortest distance between hyperplane and that data set is just this minimum value across all distances that we have. And we show this using gamma. And remember, gamma really depends on W and B because the data set is given to us. So we have this bunch of xn's, these data points. We just have to plug in here and try to find the minimum value. And that's exactly our margin gamma. And I do believe here we have this gamma represented. So that's kind of like that shortest distance. So now we're ready to kind of set up our optimization problem to solve a machine learning problem, right? That's how machine learning works. Like you need to have some criteria to optimize. So what we really want to do is we want to maximize our margin, right? Meaning that try to push away these points xn as far as possible with respect to that hyperplane. But we want to do correct predictions. And that's, again, another part that why this +1 and -1 is very important here. And the reason is that if this term here, that's sort of like our f of x, has positive sign, and yn is also +1, then the multiplication is definitely greater than or equal to 0, has positive sign too. And similarly, if this has negative sign, this W transpose xn plus b, and yn is also -1, which means that then we correctly predicted the label for this xn. Then multiplying two negative numbers, it gives us something that is positive. So you can see that in this case, we really, if you want to know if we did correct predictions or not, it's simple. Just multiply the actual label by the prediction, and this thing should be always non-negative because either they are both, if it is correct prediction, they're both positive, or they are both negative, and we know that negative times negative gives us something positive. So we are very much now ready to go to the next step. So we want to maximize our margin. This is the definition of the margin, or the way that we calculate it. And the only thing I did here is taking this W, norm of W outside, because that does not depend on xn. We can do that. And subject to these constraints that we have here, that we want to correctly classify all data points that we have. So this is part of our training data, this xn, yn. And something that is very important when you look at this formula that we have here for margin is that if I multiply both w and b by some number, let's say 2, 5, 10, anything, we are not going to change the margin, right? So the margin definition is a scale invariant, meaning that multiplying w and b by a non-zero constant does not change the hyperplane. And because of this, we have to take care of that scaling factor to make sure that we are not finding different solutions. And one thing that we can always do, we can always scale w and b such that this mean xn of this w transpose xn plus b is exactly equal to 1. So if it's not, what we do, we just normalize it to make it 1, right? It's kind of like, normalizing probability, right? If the max probability is 10 and we want that to be 1, what do? We divide that by 10, right? So that's kind of like the same exact idea here, that we can make sure that this term is exactly equal to 1 by scaling w and b, which means that now our margin that we had before is simply 1 over w, or norm of w. And this is a very important part. So if our margin now is 1 over norm of w, and we want to maximize this means that since this norm of w is in the denominator, we actually have to minimize this norm of w. And that's why you can see that now here we have this minimization problem, because if you minimize the norm of w, that's equivalent to maximizing 1 over w. And we have all those constraints that we have. Something, again, now you have to remember is that this w transpose xn plus b, since we put the minimum value to 1, then this doesn't anymore need to be greater than or equal to 0. Actually needs to be greater than or equal to what we have here, because we specifically said that, yes, we scale w and b such that this minimum value is 1. So then it's just 1, right? So that's exactly what this means. This means that everything is greater than or equal to 1. And this kind of like ensures that everything is correctly classified and outside of the street, right? So again, think about it this way. This is that line w transpose xn plus b equal to 0. That's the one that is w transpose xn, and then we have that 1. And then here, on the other hand, we have negative 1. And everything should be outside of this street that we have here. So that's exactly the interpretation of this formula here, depending on yn is positive or negative, right? So everything is pushed out of this street. Something that we have to keep in mind is that sometimes we may not be able to find a hyperplane, or in this case, this line that correctly separates all data points, right? Because as you can see here, I have these red points that's in the wrong side, right? This should be on this side, but whatever we do, we may not be able to find that. So what should we do here? So that's where we have this idea of soft constraints, or sometimes we call this regularization, very similar to regularization with L1 or L2 norm that we have seen before. So the only thing that we really do is that we had this minimum of the norm, W transpose W. Now we add a penalty term, where C is just some hyperparameter, meaning that we have to set what this C should be. So this C is not something we learn. We have to predefine this. And then we have this C times the sum of all the violations. So this Cn here is our violation for data point n. So to explain this, what we really do here is that we had this constraint before that when we didn't have this, so let's say this Cn equals 0, then that's exactly what we had before, that everything should be outside this street. Now with this negative Cn, this means that we allow some points to be inside the street. And how far they can be depends on this Cn, right? So here we have a nice interpretation of this. Again, this is the line W transpose X plus B equals 0. This is the one with negative 1 and 1, so that defines our street. So this red one here right now is on the wrong side because it should be on the right, but it's on the left. So now we know that this CI here should be something that is greater than 0 because there's a violation. And if you really want to know how much it is exactly, so this is kind of like less than 1 because we didn't pass this decision boundary yet. So overall, still we are correctly classifying this because this is the main decision boundary and this is on the right side, but it's not on the right side of this sort of like, this pink line because that's sort of like what determines what the street is. And we're trying to push everything outside of this street. And the same thing happens here with this red one. In this case, we have a large amount of violation. You can see that we even are in the wrong side of this decision boundary. So, and the same thing happens if we have like, let's say a blue point on the wrong side, then we have to consider this violation. And you can think of this is that minimizing this W transpose W is equivalent to maximizing the margin. So this is what this does, this optimization problem. We want to maximize the margin, but at the same time, we are trying to also minimize the number of violations or the amount of violations we have. So this term is C is exactly what controls the trade-off between these two terms. It's a hyperparameter. We have to set this and we have to carefully adjust this. So in order to solve SVM, we can use obviously scikit-learn. I have put the documentation here so you can see everything that you need to know about support vector machines. As we said, support vector machines that work for both classification and regression, and they have different implementations. That's why in scikit-learn, the classifier one is called SVC, support vector classifier. And the way that this works is that you can see there's the second parameter here that you have to provide, this C, is what is called the regularization parameter. Exactly the C that we had in that optimization problem that we defined. And the thing that is very important about this is that when you look at the documentation, it says the strength of the regularization is inversely proportional to C. So it is very important to understand this term. What does it mean is inversely proportional? So this means that if you look at that sort of like, optimization problem that we have here, if we have a very high C, then we really cannot have any violations because we want to minimize this entire thing. And if these CNs are also like large, then we multiply this by a large number here, and that's not good because we're trying to solve a minimization problem. So higher values of C means that we have less regularization, and this is because we have to work very, very hard to avoid all sorts of margin violations, and this can lead to more complex decision boundaries because we don't have any kind of like wiggle room here. However, lower C, for example, when C is very, very close to 0, this means that we can have a lot of margin violations. And so in this case means we can have more regularization, so we can have simpler decision boundaries because we don't care about all the other points. So we can have some violations to the degree needed. So that's kind of like that idea of like inversely proportional. So this means that if you really want to regularize this problem, you want to make C closer to 0. And if you look at the documentation, the C, as far as I know, is that it cannot be exactly 0. So you can see that it says must be strictly positive. So for example, you can choose 0.00001, but it cannot be exactly 0. The other thing which is very important, because you know that in most cases, important parameters are at the beginning, is this kernel function. So what does this mean? Linear polynomial RBF, which stands for radial basis function. So the reason that support vector machines, they gain a lot of attention is because they can solve both linear and nonlinear problems. And you may wonder why or how. So remember, the way that we define support vector machines so far is based on this decision boundary, which is this hyperplane, right? Which is this vector W and this bias term B. So it appears that if we use what we call as the dual formulation of these, and we can write our optimization problem in a different form, where this f of x has this, again, bias term or constant plus the dot product or inner product between this x and all the training data points, these xi's, and each one needs to be scaled by some alpha, and that's why we show this alpha I. So each xi or training data point or observation needs to have its alpha I, and then we have this dot product and then multiply by this alpha I. So alpha I in some sense measures how much xi can change the decision boundary, because that's the whole idea here. We have these support vectors. So in practice, we don't want to let all data points impact the decision boundary, only a small portion of them. Those things that we call support vectors that are closest on the both sides of the decision boundary. So with that, now you can see that we have this dot product or inner product, and we can technically find new representation or mappings of these original data points into some very high dimensional spaces where it's easier to separate these data points and then find the dot product, right? So we basically have a dot product in a higher dimensional space. And it seems that there's a very nice way of doing this using something called kernel trick, where the only thing we really have to do is to replace this dot product here with this kernel function, which in some sense measures similarity between x and xi. So in linear case, this kernel function is simply the transpose of the first vector times the second one, so the dot product. In polynomial kernel, we have a polynomial function, so we find the dot product plus some constant raised to some power of d, so it's a polynomial. And with the radial basis functions that are very popular in this domain, we use this exponential function negative gamma and then the Euclidean distance square between xi and xj. So if xi and xj are exactly equal, then we get exponential of 0, which is 1. And then if this distance increases, then the value goes down. So that's what I was saying, that kernel functions can be viewed as some form of like similarity between data points. And here is then the idea. So if you use the linear kernel, you're going to find those linear like decision boundaries or hyperplane. But you can also use some other types of kernel functions to find nonlinear decision boundaries to separate classes. And there are options here too, that if you choose polynomial kernel, then there's a degree parameter. With RBF, there's gamma, which is exactly the gamma that we had there, to decide what it should be this parameter when you define these similarities and so on. So now let's look at the example of these and see how support vector machines work and why they're different than, for example, logistic regression and some other methods. So this is based on this official documentation or example from sklearn. I put the entire sort of like link here if you're interested. I just made a few changes and added some comments to make this a little bit more clear what we are doing. So sklearns are inside SVMs, sklearn has a module called SVM. So that's where here you can find SVC, which is support vector classifier. They're included inside this module. We work with a synthetic or artificially generated data, work with 40 data points. 20 of them are centered at these -2 and 2, and then another 20 of them are centered here. So the goal was to kind of like have some sort of like, close sort of like distance or overlaps between these two classes, but not like super close. So you can see that in this case, we have two blobs or clusters, one around -2 and 2, and the other one around 2 and 2. And the first ones, they all belong to class 0, and the other ones belong to class 1. Then the main thing I want to emphasize here is when you use this value of C, which is high, this means that we are not regularizing. So that's why I call this unregularized. And then when C is small or closer to 0, in this case, for example, 0.05, then means that we are doing regularization. So as we said, the first thing is to import SVM, and then inside SVM, we have SVC. And for now, let's consider linear kernels, and I want to just show you the impact of this C. So very similar to other machine learning methods in sklearn, we use clf.fit, we provide the training data, which is in the form of input-output pairs. So how can we find the decision boundary? We can actually, since now we know the mathematical foundations of support vector machines, we can solve this problem. So let's say if we have W0 times X0, or whatever our x-axis is, here I'm showing you this with x plus W1 times the second dimension, which I show here YY plus B, we can find, we can assume that x is our independent variable and y is our dependent, and we can use this equation. So in this case, we are going to look at the coefficients of our classifier. So this is our attribute. And this W now is going to have like two elements, right? Because we have W0 and W1. And we need to find this negative W0 over W1. So that's this line here. And what we have here. And then we have this B over W1, which is our intercept divided by W1. And now we need to find the margin that we have here. So you can see that now the margin here is technically 1 over the norm of W. And in order to find the norm of W, you can square each element, add them together. So that's norm square. And then we have to take the square root. And then we go plus margin and minus margin to find that street that we talk about. And in this case, obviously, we can draw these lines that we have for our decision boundary and those two sort of like, parallel lines that we have. We can also identify our support vectors. This is given to us when we train a support vector machine classifier. So that's where we plot our support vectors. We do plot our data points because we want to have everything in one figure where we can visualize how things work. And then we have these sort of mean and max values for our x and y axes. And the only thing that we do here, which is kind of like, extra or additional, is that we also want to have a nice visualization of what we call as the contour plots, or how these sort of like, classes differ when we move away from the decision boundary. So that's why we use here. So we can always remove this if you don't want to use this one. That doesn't really change anything, but it gives us a little bit better visualization with these colors when I plot this. And since everything is in a for loop, so one time we're going to use this value of penalty 1. That's the first figure we get, and then we use 0.05. So let's run this cell. And here's the result that we get. So the colors you can see here, that comes from our contour plot. So if you don't want to get those things, you can always remove this part of the code. But I personally like them. I think they make it like nicer to visualize how here everything works. So this line here that you can see, this solid line, this is our decision boundary. So that's that line W transpose X plus B equals 0. And then we have those two parallel lines, W transpose X plus B equals 1 and -1. So those are the parallel lines, these dotted lines that you can see. And you see that these sort of like, points here that we draw another circle around them, these are our support vectors. So this means that the way this works, we are trying to maximize the margin on both sides. We have this line right in the middle of the street, and then we have the same distance here if we project this perpendicularly here and this one here. So that's why we had to discuss about finding distance of a point to a hyperplane, right? Because the distance is this, when we do this perpendicular projection, and the same thing here. And obviously you can visualize these here and see these two are equal, these distances. So C equals 1 means that we are kind of, strict about any kind of violations, right? Which means that we are not really regularizing very much. So what does happen when we regularize a lot? And in this case means that C should be closer to 0. And that's what happens. This means that now we allow for some violations. Originally, we didn't want anything to be in this street, right? So it's like a two-way street, remember that? And now we have some of these blue and red ones, right, that are inside this, the street that we have. And that's because we use this C equals 0.05. So this is really nice because now we can, look at different cases. I definitely encourage you to experiment with the code here. What happens if I make C really, really small? Then probably we get a lot of violations. Let's see if that's the case. And you can see that, yeah, now basically all of these points are violating because it's all inside the street. And you can see that we have these circles around them. So you can see that in general, it's not a good idea to allow too much regularization, but it's a good idea to have a little bit just to allow for some sort of like, room for mistakes if really need to be have those types of things. Whereas when we C equals 1, you can see in this case we didn't have much regularization, and the goal was to make sure that we have this street where we don't have any data points there, but you can see the trade-off. Now this street is kind of like narrow, whereas this street is kind of wider here, right? Because now we allow for more violations. So that's the role of the parameter C that we have to set, and because of that, it's called a hyperparameter. Now let's look at the role of the kernel function. In order to do this, we use this against symphytic data set because I want to make sure we look at two-dimensional spaces so we can exactly see this line and a straight line that we have. And in this case, we actually want to make this a straight line to be a nonlinear function. So that's where we're going to use that kernel trick that we mentioned, where we swap the dot product with some kernel function. So obviously you cannot just find a line here to separate these two classes because we have this nonlinear structure here. And we do create this using these make moons. We create 100 data points with some noise level so that tells us the separation between the two classes. And here also what we really want to do is to make sure that we first standardize our features. So we create a pipeline, we standardize our feature, and then we use this SVC with RBF or radial basis function. And in general, now since, in this case, for the kernel function, we have a gamma parameter. So we have to set some values for gamma and also for this C. So first I'm going to put C to 10 to the power of 5, 100,000. So this means that we do not want to regularize right now. We want to solve this problem to the best we can where we correctly classify points and no margin violations. So in this case, we train this model using .fit, and then I write some functions to plot this data. So this is for like our scatter plots, and also to be able to use those contour plots to be able to see how the decision boundary looks like. Because here the decision boundary is nonlinear. You cannot really even like use the formula I gave before. So the best thing is to just look at the prediction of your model and then use these contour plots. So now if I plot these sort of like contour plot here, so you can see that now we have these two classes, right? Class 1 and -1. And because we use that nonlinear kernel function, which was that exponential of negative gamma, the distance between xi and xj, we can find this very nice looking decision boundary, which can be very complicated to mathematically represent it, but we do not need to do that because we use kernel functions and just swap a dot product with a kernel function. And you can see that here we correctly classify all these data points, even though this decision boundary should be very, very complex. And that's what I was basically mentioning before. That really depends on this parameter C for regularization. Let's set this to be like 1e negative 5, which means 10 to the negative 5. So this is now super small. And I run this cell again. And we plot now this decision boundary. And you can see that now we are making some mistakes. The green one, right? These green data points are on the wrong side. These blue data points are on the wrong side. But at the same time, you can see that this decision boundary is much simpler. It doesn't have all those, sort of like oscillations that it had to have before to be able to correctly separate these. So overall, this is a simpler decision boundary. And this is because we regularize this more, meaning that we can have more violations in terms of not correctly classifying all data points. But since these models are very powerful, such as support vector machines, this means that yes, theoretically, we can, in many cases, correctly classify all data points, as you can see here. But this comes at the cost that we have now a more complex decision boundary. So that's kind of like why support vector machines are very popular. They can be extremely powerful, but remember, at some point, we may not need to have a very complex decision boundary because we care about the generalization or how our model performs. And in those cases, it's a good idea to use regularization. Finally, I want to very quickly talk about support vector machines for regression. We don't want to go through all formulations, but the best way to think about it is that I mentioned before that we talk about support vector machines in classification settings as having that street where we want the data points to be outside of that street. So in regression, we want to really do the opposite side because we want to explain the data. We want to make sure that as many instances as possible are actually on the street without having a lot of them to be outside the street. So it's kind of like related, but in a little bit different way. We want to now have more data points in our sort of like on this street that we have when we find these margins. And you can use this SVR, where R stands for regression, instead of SVC, that you can use. And you can see that this is the documentation page here for SVR. And one of the most important things here, I would say, I mean, we have obviously kernel and things like that that we know, but is this idea of epsilon. So what is this epsilon? So I like to think of these as epsilon tube. So it basically tells us when we don't have any penalty, if our predicted value is within some distance of the actual value. So this means that when you think about it as, let's say, mean squared error or things of that nature. So if in this case, since we have a regression problem, we have continuous labels. And if our predicted label or predicted output is within this epsilon tube or epsilon neighborhood, then we don't have any errors. And if it's outside, then that's when we start to having errors. And that's how we make sure that everything is on the street to the degree possible. In order to examine these, we create again our synthetic data, since it's just easier to explain things. We have a 1D input feature X. And one thing that we do here is that we create these 100 data points, and we also multiply this by 5. So this way we get numbers from 0 to 5. And we sort them, so it makes it easier to plot. And we use here a nonlinear function. So the true relationship between inputs and outputs is based on this sign function. And we know that this is nonlinear. We add some noise to make this more interesting. We divide our data to training and testing sets. That's something we usually need to do. And then we look at 3 types of support vector regression models with linear, polynomial, and radial basis function. And as I said, there are like basically 2 things that are very important. C, which shows us the amount of regularization. And here we choose C equals 10, which means that it's a high value of C, so we don't want to regularize, meaning that try to get the best result that we can without any violations. And that epsilon is for that sort of like epsilon tube that we discussed. So we do feeding. We are going to now plot our functions that we find for predicted values. So basically our prediction lines. For a linear function, obviously that's a linear function, but we have also some nonlinear versions due to the use of polynomial kernels and radial basis function kernels. And we do the scatter plot of all the data points and plot these 3 prediction functions. And if we look at the result here, as you can see, when we use a linear kernel, we are finding a line. We're in a 2D space, right? And that's the line that best describes this data, which makes sense. It has negative slope because of the way that this sign function here is. And then you can see that we have the blue one, which is for degree, like almost looks like a degree 2 polynomial, right? So it tries to kind of like explains the data. But then when we use RBF kernel, because RBF kernels are based on that exponential functions, we even get more sort of flexibility. So you can see that this green one, or green prediction function, does a relatively great job of explaining this entire data set. So it means that in this case, we could even be able to find something that explains a high degree of nonlinearity. And but at the same time, you can see that this red one, which is the linear kernel, does not work well because it just finds a linear function, and we know that sine function is, not well represented by a linear function. So we can always see here, I recommend you to practice this with working with different values here. So what happens if, let's say, I change the C value and make it very small, like 0.001. So in this case, we regularize a lot. So is that too much regularization? Let's see. Yeah, it looks like it. Yeah, so you can see that in this case, especially with the red and the green one, like the linear RBF kernel, we regularize so much that in some sense, we let our model to do whatever it wants, and it's not anymore encouraged to able to fit to the data that we have because we allow for a lot of regularization. So you can see that in general, this C should not be too small, right? That's definitely a problem, right? So if I put this back, so you can see that now if I choose that C equals 10, we get much better results. Obviously, in a real world problem, you may not be able to visualize. You have to look at metrics such as mean squared error, coefficient of determination, explain variance, and so on and so forth. But right now we can visualize things, which is nice. And the same thing happens with epsilon, right? So you want to make sure that this epsilon is not too generous. If it's too large, that means that, we are not penalizing the model enough. And you can see this is happening here, right? So again, with the linear one, doesn't change very much because in general it's not a good model. But you can see, especially with the more powerful model, which is the RBF kernel, you can see that now it's not really motivated to approximate this function very well, because now we have this epsilon tube that is too large. But if I put it back to something smaller, you can see that we get a much better result here.